Hi, I'm Nathan, and my research establishes computational principles that enable general assistive robots to adapt to specific end users by framing this as a form of multimodal communication. Robots are fundamentally different from computer-based AI systems because of their physical embodiment. A robot's embodiment gives it access to additional embodied channels of interaction like eye gaze, facial expression, and movement, but robots are often taught through AI techniques that were created for computer-based interactions, which underutilizes the rich embodied information that humans naturally emit. Design communicates a promise to the user about what a robot can do, but understanding what those expectations are is unclear. Luckily, people automatically associate new designs with familiar concepts to ground expectations. These associations are called design metaphors. The first part of my dissertation assembled a dataset of robots and their design metaphors to understand people's social and functional expectations of robots. I found that metaphors significantly affect users' expectations, and semantic metaphor relations induce corresponding changes in user expectations. Beyond mechanical design, I also created a methodology for using clothing to modify a robot's embodiment and developed open source tools for anyone to start developing embodied social agents, which has been adopted by several universities internationally. A robot's design communicates expectations at the beginning of an interaction, but during interactions, users communicate through physical communication channels. I leveraged physical communication channels to help users perform rehabilitation exercises. This robotic system consisted of a physically assistive robot to provide reaching targets in 3D space, and a socially assistive robot that provided instruction and support. By logging the arm choice users made when performing this exercise, I was able to learn a user model that provides a metric for arm non-use, an important measure for determining how much therapeutic outcomes transferred to real life. This method was correlated with existing clinical measurements, but shows a higher test-retest reliability and is easy to administer. This same robot can also be used for physical care tasks. My dissertation introduced the first formulation of robot-assisted hair care for users with limited mobility by estimating the structural gradients of the user's hair from an image. This allowed users to communicate how the robot should comb their hair through clicks on a live video. In addition to physical assistance, robots can use embodied communication to socially motivate users. Users implicitly communicate their motivation through engagement in a task. And robots can use social actions like rewarding, encouraging, and clarifying statements to causally influence a user's engagement. In a gamified rehabilitation exercise for youth with cerebral palsy, I learned models of user engagement dynamics and showed how those dynamics models enable robots to optimally provide social feedback, resulting in higher user engagement levels and promoting positive therapeutic outcomes. I also showed how other unstructured social interactions like exploratory search can create better robot trajectory representations to design signals in assistive item retrieval tasks. By thinking of robot adaptation as communication, we can efficiently adapt robots to better assist people in accomplishing their own unique goals.